Good afternoon, everyone. Welcome back to the Einstein Toolkit meeting, and good morning to Zach and Steve and Peter to the US people, and in some regions, good evening to you. Zach, for those of you who don't know Zach Etienne, we will be hearing a tutorial from Zach Etienne, and he's a professor of physics at the University of Idaho. He is a maintainer of the Einstein Toolkit. His research includes binary black hole mergers, binary neutron star mergers, and black hole neutron star mergers, and also distributed computational citizen science. We will be hearing a tutorial on NRPy, and thank you, Zach. You can take it from here.
Great. Thank you, Behan, and thanks for the invitation to, well, really it motivated me to put together as you can see from the title of my talk here, the NRPy tutorial, which we'll get to at the end. So I wanted to start with a presentation I'm sure you've heard this story before, but it bears repeating because this is the story of numerical relativity and its most important role, in my opinion, to modern science, and that is its role it plays in gravitational wave astronomy. How it plays a role is very interesting and somewhat nonlinear. It plays a role in gravitational wave astronomy through a process known as parameter estimation, whereby we compare, not we, but the community compares each observed gravitational wave signal to millions of theoretical predictions. Now, for those of you in the know, you're quite aware that there aren't a million numerical relativity simulations of, say, binary black hole mergers. So how do we square this circle? Well, these catalogs are actually used as a ground truth for what are known as gravitational wave approximants, which are at the heart of gravitational wave data analysis. So if that's the heart, then this is, well, the heart of the heart, okay? These numerical relativity binary black hole simulation catalogs. And we've been doing great with the current state of the art with current generation gravitational wave detectors, so-called 2G detectors. But looking ahead at the next generation of gravitational wave detectors, we know that our existing catalogs are insufficient. That, in fact, the dominant error source in our data analysis is not the gravitational wave detector itself, but numerical relativity simulations. We are standing at a cliff that we need to cross to the other side, where we need to fill the gap, 10 times more accuracy, and we need larger catalogs because of the more diverse binary scenarios that these next generation detectors will be capable of observing. So I'm underscoring here the fact that we need more accuracy and to get more catalogs at reasonable computational cost efficiency. So at the heart of NRPy, sorry, I keep saying at the heart of, but in NRPy, there is a native numerical relativity code. It's called Black Holes at Home. We will go over the fact that NRPy also is quite capable of generating Einstein Toolkit modules. Sorry, there's something in the chat. Yes.
We will be monitoring the chat, yeah. We will monitor the chat, yeah.
Please do raise your hand or just speak up. It's totally fine. All right, so like I said, the core numerical relativity code in NRPy, its native language, if you will, its native code is Black Holes at Home. And what Black Holes at Home aims to do is fit the binary black hole problem on the consumer-grade desktop computer, and not just do that in a way that is just a proof of principle, but do real state-of-the-art numerical relativity simulations on consumer-grade resources to benefit next-generation gravitational wave astronomy and current generation, to be honest. So the basic idea behind Black Holes at Home is, while I know and love and continue to use on a daily basis within my group, Cartesian adaptive mesh refinement grids, they're not by any stretch optimal for simulating compact binary systems. After all, black hole and neutron star gravitational fields, hydrodynamic fields, don't look very box-like. And you get these factor of 2 transitions in resolution that I've shown are actually, when interacting with the sharp gauge feature in early binary black hole evolutions, cause reflections and result in more than 99.99% of Einstein constraint violations. So that's a big deal. So what black holes at home is based on is first a covariant form of one of the community's favorite or most widely used formulation of Einstein's equations, BSSN. By the way, if you've heard the term Z4, Z4c, it's a very close relative of BSSN. So this formulation was developed by Brown. What it enables is the construction of Einstein's equations, symbolically at least, mathematically, in any coordinate system you like. So it makes what was originally designed for Cartesian basis tensors and vectors and generalizes it to spherical coordinates, for example. Baumgart, Montero et al. Extended on this work, built on this work a few years later, coming up with the first ever fully stable numerical relativity code that works in spherical coordinates with the same robustness and stability as Cartesian. I know it sounds remarkable, but it's true. And you don't have to go far to reproduce these results. You can download NRPy and immediately perform numerical relativity simulations in spherical-like, Cartesian-like, cylindrical-like, a large class of coordinate systems. NRPy is capable of constructing Einstein's equations in. So what black holes at home does is it builds on this idea that these fields are not box-like, and the fields also don't exhibit factor of 2 transitions in length scale, which is what AMR grids would be sort of optimized to model. So the idea is with these special coordinate systems and multiple patches, multiple coordinates, exploit near symmetries. In other words, where things are nearly spherically symmetric, you have high radial resolution and low angular resolution. By doing this way, you are then able to battle the curse of dimensionality directly. And when you tackle that issue specifically, buckle up, because it's going to be a potentially huge reduction in computational cost. So this is a picture of a numerical grid structure that black holes at home uses. You can see here there are 7 independent grids. One feature you'll notice is that there's no r equals 0 in any of these spherical coordinate grids. That's intentional because this time step of a numerical relativity simulation is governed by the smallest grid spacing. And well, when you have enormous focusing of grid points near r equals 0, as you would in spherical coordinates, that would cause your simulation to become very slow, this is exactly why you don't see, beautiful spherical grids around the black holes. That said, these grids in between the black holes and out to the outer boundary make black holes at home so efficient, I'm able to perform binary black hole simulations on par with, in terms of numerical noise and errors, any numeric relativity code you throw at it, in about 3 gigabytes of memory. That's about a factor of 100 less than a typical adaptive mesh refinement simulation. that just uses boxes. And it's about a factor of 40 less in CPU cost. And that's using the substepping in time comparison with the Einstein Toolkit. So we've accomplished some important science with black holes at home so far. In our first binary black hole catalog that we produced purely for internal purposes, we performed of order 100 binary black hole simulations. And in that, given that I was just running on a supercomputer because, well, I'm in debugging mode and I want as fast a turnaround as possible. But each node in that supercomputer was running an individual binary black hole simulation. With that ability to run 100 simulations with 100 nodes gave me the opportunity to experiment with new techniques that had been on the back burner for years. And with this, I use black holes at home to reduce numerical errors in binary black hole simulations, tackling this problem I alluded to earlier. We have a sharp gauge feature that propagates out from the black holes and contaminates the resulting simulation. Again, being the result of 99.99+% of constraint violations. So this is accuracy. This is without increasing numerical cost. These techniques, it's just a tweak to the gauge conditions, which are free to choose for the most part. But the overall cost is way less than 10% of the overall runtime. And you drop your numerical errors by orders and orders of magnitude. Also efficiency, like I said, these performing binary black hole simulations on this type of grid structure enables you to fit and sample the space-time in only 3 GB of memory. That's enough to fit on my cell phone. So with this capability, my goal is to democratize numerical relativity, where before it's been said, to do numerical relativity, all you need is a supercomputer and a dream. Well, what if we got rid of the supercomputer from that equation and enabled state-of-the-art numerical relativity, binary black hole simulations, the most common gravitational wave source, by the way, to be performed on desktop computers. So our plan is to launch a numerical relativity, the first ever numerical relativity volunteer computing project, get the public involved, and build the largest ever state-of-the-art binary black hole gravitational wave catalog. And here is that picture I showed from my first slide. You can see looking down at the orbital plane on roughly, I think this is not the full set of simulations I performed. It's more like about half. Yeah, please.
So like I think you should stop your sharing the screen. My voice is coming.
Oh, you hear an echo?
No. Your screen share is stopped, I think.
Okay.
Oh, my screen share stopped? That's weird.
Yes.
Okay, well, I'll try it again. Just a second. Sorry. Can you see it again?
The last thing I saw is that you showed accuracy and your paper in PRD in 2024. Is it correct?
Yeah, that was pretty close. Can you see my screen now?
I don't see any change. Maybe that's from my side. I don't know.
Oh, that's
No,
weird.
I see the black holes at home slide with the accuracy thing on it. That's what I see.
It just says
Yes.
accuracy. It doesn't say efficiency. Okay.
Doesn't say
Wow.
efficiency, it just says accuracy.
Dang. I'm sorry. That's weird.
Maybe
let me
stop sharing. Yeah. Maybe stop sharing and then reshare.
Yeah, I want to do that.
Now you can.
Yeah, thank you. Okay.
Yeah,
Can
now
you
we
see
can
that?
see it. Yes.
Okay. It's interesting. It actually shows a yellow border around it when this sharing is disabled. Interesting. Okay, turn off
Sorting
that.
that. Yeah.
Heck. Okay. Please. Okay, I don't want. Okay, that's better. There we go. All right, let's get back to it. All right, so like I was saying, efficiency, so that you can fit binary black hole simulations on a desktop, 3 GB of memory. The goal is to democratize numeric relativity, and with that capability, launch the first ever numeric relativity volunteer computing project known as Black Holes at Home. So here you can see on the left some of the beautiful binary black hole trajectories. This is a subset of the 115 reproductions of SXS simulations, so performed by the spec code from the Simulating Extreme Spacetimes collaboration. So I reproduced these with black holes, and I'm using the same initial data parameters, although unfortunately I wasn't able to perform with exactly the same initial data because those are not public. So I just used the 2 punctures code, ported over from the Einstein Toolkit into Black Holes at Home to do this. And you can see some beautiful dynamics here. Orbital plane, this is like 30 or 40 of the simulations overlapped, the trajectories of one of the black holes in these simulations. And you can see that some of these are very highly processing binary black hole scenarios. Precession in a binary black hole in spiral, it's one of the very beautiful effects predicted by Einstein's equations of general relativity. Similar effect is what causes the perihelion precession of Mercury, but when you have 2 extremely curved space-time phenomena known as black holes spinning, they can actually pull each other due to their spins being out of misaligned, let's say with the orbital angular momentum. You can actually pull, the black holes will actually pull themselves out of the initial orbital plane and into this cool precession, that you can see here on the lower left plot. So like I said, with that first simulation campaign, we developed new moving puncture methods, reducing numerical errors by orders of magnitude. And in my paper, I demonstrate that these techniques are applicable even on Cartesian adaptive mesh refinement and have similar orders of magnitude drops in Einstein constraint errors. But it also uncovered, because of course these were like debugging runs for Black Holes at Home, it uncovered a few issues. First off, NRPy, being the first Python code I ever wrote, wasn't very Pythonic. If you know about Python, you know what I'm talking about. And as a result, it looked like a code written by a C programmer. So using a very small subset of the capabilities of the language, and just being a bit cluttered. So the bottom line is, it became very painful to work with Black Holes at Home. All the things we had planned for Black Holes at Home, and most of these have come to fruition at this point, including a NPI parallelized version of Black Holes at Home for extreme binary black hole scenarios, GPU capable Black Holes at Home. So it seems silly that we're going to be running on consumer grade devices, but on the slower processing unit in their computers. So the goal is to have Black Holes at Home run on GPUs as well, and various other goals. So in order to make that possible, other people need to work with NRPy, and the NRPy 1.0, as I call it, was not very conducive to, it wasn't as modular as it needed to be, basically. And I'll talk about that in a minute. But second, and perhaps most importantly, was these simulations, many of them are stopped because there was an instability. I'll talk about that in a minute. Another issue that was revealed was, yes, it's amazing to package the Einstein Toolkit with Black Holes at Home. We needed it because that was the only apparent horizon finder that we could get our hands on easily. But there are some real issues with there's some real conflicts with our goals and ambitions of running on even Windows computers, not just Linux, and even running on small, very meager consumer grade devices like tablets or even cell phones. Getting the Einstein Toolkit to even compile there could be problematic. So I've spent the last couple of years working on, few years actually, working on these three issues. So first, let's talk about NRPy needing a refactor. So we went from NRPy Plus, which was aka NRPy 1.0 to NRPy 2.0 a couple of years back. What NRPy is capable of, generally speaking, it converts SymPy expressions whereby you construct symbolic complex tensorial expressions using Einstein notation. So it's very easy to convert between what you're typing and what is in the scientific paper. And what it does is it takes those expressions and doesn't just spam it out into a gigantic expression in C code. It actually pipes it through NRPy's and SymPy's C code optimizers, including common subexpression elimination, which we'll see in a little bit, as well as single instruction multiple data. So leveraging some of the state-of-the-art features on modern day CPUs, which these two combined improve the performance of, say, a numeric relativity code, evaluation of Einstein's equations by over an order of magnitude easily on modern day CPUs. Without this, you're going to have a very, very slow code, and it's going to be very difficult to do science. Black holes at home would not be possible without these optimizations being there. And it's all this optimization is done automatically, and we've shown it to be. I've not seen a head-to-head comparison where NRPy loses the battle of speed. It also it generates black holes at home. Oops. It generates black holes at home. Like I said, black holes at home is NRPy's native numerical relativity code, numerical relativity infrastructure. It has all of the components of black holes at home, including reference metric formulation and many other aspects. NRPy Plus, NRPy 1.0 consists of a few core Python modules, I would say of order 20, and around 100 Jupyter notebooks. No joke, 100 Jupyter notebooks. And we've been very, very careful that these Jupyter notebooks have been well curated and contain consistent formatting. Like each one has a table of contents, an abstract, a title, and every section is clickable, small, easy to understand. I know of many students who have learned numeric relativity with the benefit of having these Jupyter notebooks. So I'm actually going to reveal today for the first time the NRPy 2, as in the number 2 tutorial, where I'm now moving over, finally migrating these Jupyter notebooks over to NRPy 2. And yeah, so we had big plans with NRPy Plus, like I said, getting NRPy to generate kernels for GPUs, making black holes at home work on GPUs, making it work on high performance computing clusters, so we can tackle not just extreme binary black hole scenarios, but also with the incorporation of GRMHD. Leo Vernick will be giving a talk, I believe it's tomorrow, on Grail, our new GRMHD library for numeric relativity. It's like a numerical recipes for GRMHD. With Grail and the new NRPy 2.0 version of black holes at home, my student Terence Pierre Jacques was able to take that vacuum code and make it work completely fine with GR hydrodynamics, with tabulated equations of state support and neutrino leakage in only about 1 month. Okay, that's huge, huge time savings. So the problem is these plans conflicted seriously and severely with the just the code structure of NRPy 1, NRPy Plus, NRPy 1.0. And so looking ahead with that capability, I was faced with this.
What's your prediction for the fight? Prediction? Yes, prediction.
That was my prediction for going, adding all this stuff to NRPy 1.0. So I made the decision to work with NRPy 2.0. This is another, I think, very, very insightful. I hope everyone was able to hear that. Behan, were you able to hear that?
Yes,
video?
yes, we can hear that. Yeah.
Perfect. Okay. So here's another very, very informative, instructive, and sage video.
Every single software project follows the same rule. The first 2,000 lines, it doesn't matter whether you handwrite it or you vibe code it, it's all the same. If your project's only 2,000 lines of code, it's easy. But once it starts growing, once it gets past that, something kind of magical happens. And at 10,000 lines is where the maximum magic is. And what is that magic, of course? It's the y-axis, which is regret. You regret every single decision you made during these first 2,000 lines when life was good and coding was easy.
So another way of putting it was I felt regret in how NRPy 1.0 was designed. And I didn't want to have to deal with that moving forward.
See.
So NRPy 2, same capabilities, core capabilities, highly optimized C codes. It's much better written. It's properly Pythonic. It's something you can pip install, which is awesome. Pip install NRPy. Now we'll get NRPy working immediately on your local computer. You can do binary black holes, well, head-on collisions on even cell phones. It works just fine. Generates black holes at home, blah, blah, blah. Completely refactored and therefore much easier to extend. Here's a picture of the GitHub. And again, pip install NRPy. Unfortunately, this version, I haven't updated the PyPI version of NRPy in a while, but yeah, there's another pip install command that will enable you to install the latest version on Git of our main branch. And that will give you something so much more. This is probably over a year old. So much has happened in the past year. So with this capability, the capabilities offered imbued into our group by NRPy 2, we've now built some really amazing machinery, including Groovy, which is Terrence's baby, general relativistic hydrodynamics with tabulated equations of state, neutrino physics, with using black holes at home. So this is our black holes at home, if you will, geohydrodynamics code. We have GPU capabilities. So we were able to get black holes at home up and running on consumer grade GPUs, and compared to consumer grade CPUs, so say an NVIDIA 3060 or 3070 as compared to a 16-core high-end Ryzen 9 CPU, it's something like 5 to 10 times faster to do the same numerical relativity simulations. It's solving full Einstein's equations. Another key development, and notice the years here, they're all very, very recent. So a lot we've kind of had a watershed moment in the history of NRPy with getting out some really amazing tools that can do cutting edge science here. So Superb NRPy, so this is our task-based parallelized version of black holes at home. So Superb stands for supercomputer ready black holes at home. And this is Nishida's project. Sorry, the previous one was Samuel Tootle's project. And that was also recently published. Terrence has actually, since these, it took him a grand total of 2 weeks to incorporate Groovy into Superb. And with that capability now, he's able to run and do state-of-the-art simulations. He's doing bar mode and stable neutron star simulations with tabulated equations of state. So really exciting science happening there. All right, let's move on. Okay, where am I at here? Okay, Yes. Okay. So NRPy needed a refactor. That was fixed, and a lot of great science has come out of that. I'm going to tell you a little bit more science that's come out of this as well. One of my own papers, and we'll get into that in a minute. Next, let's talk about the instability. Okay. No one has ever solved Einstein's equations on this type of grid structure before, and therefore it wasn't known a priori if there might be some issue. The issue, unfortunately, is the most annoying type. So if you look here, here is the Einstein constraint, the Hamiltonian constraint violation in the region, basically excising the interiors of the black holes in the region from 0 to 20 M. So this is a strong field region of our binary simulation. And you'll see, if you know how to read these guys, the total mass of the system is 1 in code units here. And so this is very, very low constraint violations. This is state of the art, if you will. No problems whatsoever. And you can see here we're evolving these binaries out to beyond 4,000 M. You need roughly 10,000 M to do a lot of orbits, to do sufficient orbits to do real catalog generation. We were doing just fine. Things were going just great. Here's the wave zone. You can see here a jump in constraint violation early on. Every moving puncture simulation sees this. I would bet every even generalized harmonic simulation sees a big jump in constraint violations from the initial data in the wave zone. So this is between 100 M and 500 M. And you can see that this is all entirely due to that sharp gauge feature, which was greatly smoothed out, but still there's a big jump. And after that passes 500 M or so, you can see the constraint violations go right back down to the very reasonable levels. Again, nothing at all here to be worried about, nothing even to write home about. This is really, really great looking. But now when we look in the region, this is all physical, the domain of physical interest, right? The strong field to the weak field, 500 M away. The issue happens at the outer boundary. And it only happens in a fraction of the cases, but it's enough to not want to launch a volunteer computing project when you have over a 20% chance, not 20%, no, this is 4 out of 23. So yeah, I guess it's about a 20% chance of your simulation dying prematurely. So there's trouble at the outer boundary, very annoying. And after months of digging into this and trying to find an easy solution, I didn't find an easy solution, unfortunately, but I did find
Zach,
yes, please.
Steve says that I'm assuming that -5 means 10 to the -5 in the
Indeed, yes. Sorry, yes,
yeah,
that's right. The axis here is log base 10. Sorry, I should have fixed that. Anyway, it's log base 10. So these are very, very, very small constraint violations. But it also means here you're seeing an exponential rise in constraint violation before it crashes. So the trouble is at the outer boundary, and what this and the cause of it is simply this: how the multi-patch infrastructure worked was, as the black holes orbit, the entire grid structure orbits with them. So you can see everything all the way to the outer boundary. And what we found is that sometimes interpolations amplify noise exponentially on the z-axis near the outer boundary. So because the entire, we're talking, this is going out to like 1,000 M.
You have sorry, you have an axis in the grid on the outer boundary?
Yeah, exactly. So this is in spherical coordinates, and the line piercing the centers of these two punctures going out, that's actually the z-axis of all the spherical coordinates grids that you see here. So yes, there's a z-axis up here at the outer boundary, and that turns out to be problematic. There's a high density of points on the z-axis, and effectively what happens is information propagates faster than the CFL condition would allow. It's still, the CFL allows for super duper luminal waves to propagate very far away, but because the grid is moving, there's a high density of points along the z-axis. This is what ultimately causes this issue. And I found that if I minimize, if I choose the regridding threshold, so remember, we're regridding here. We're interpolating all the data on this grid to this grid, basically, as the black holes orbit. And what I found was if I set my regridding frequency just right, such that the interpolation error is minimized, right? The interpolation error is always minimized if your source and destination interpolation points are the same. So if you choose an integer number of grid points out here to set your regridding threshold, then things can stabilize. I don't want to have to do fine tuning in a volunteer computing project where we need to do thousands of simulations. So again, that's a no-go on that front. So, and by the way, here is what the numerical grid structure looks like. And what I have done in NRPy 2 is implement a new version of this multi-patch infrastructure such that this is possible. This is actual grids generated by the latest black holes at home. So you can see that we now have a sliding boundary, so that outer boundary issue is ameliorated. There, it's completely fixed in time. Oh, nice. Look at all those slides I put together. Nice. So there's your animation. I'm just going back and forth. Sorry, the black holes don't actually go back and forth, but I'm just showing you that there is a sliding boundary. So that is fixed. Bottom line, I've actually done some simple simulations with that fixed outer grid, spherical grid, and things are very stable. The next thing that we have to confront is the fact that we depend on the Einstein Toolkit, and the Einstein Toolkit unfortunately does not compile on every operating system. In fact, something like 70% of operating systems on desktop level computers are workhorses here for black holes at home run Windows. So the dependency comes from the fact that the black holes at home needs an apparent horizon finder. You really don't want to be doing numerical relativity simulations involving black holes without some sort of a horizon diagnostic, like an apparent horizon finder. It provides some very important black hole diagnostics, like I said, including the coordinate shape of the horizon, which is super important if you need to dynamically adjust your grid around the black hole. Turns out in the moving puncture gauge, a spinning black hole will squish along the direction of the spin axis. And for really highly spinning black holes, that squish can be very, very pronounced and result in a very highly ellipsoidal black hole. What you want to do is adjust your grid structure near the black hole, each black hole that's highly spinning, to be squished exactly in the direction of the spin axis. And that is most optimal. So in order to know what the coordinate shape of the black hole is, you need apparent horizon diagnostics to do that. That's just one example. You can also get from the apparent horizon finder actual measures of the individual black hole spins as long as they're far apart or after merger, and also their masses, their irreducible masses. So the idea was we would just use H-Finder direct from the Einstein Toolkit. The issue is with that approach, I know of people who have done this, and I know it takes many months to accomplish this, but you can't get the apparent horizon H-Finder direct, the apparent horizon finder, the state-of-the-art apparent horizon finder, H-Finder direct. You can't separate it from the Einstein Toolkit. Not easily, at least. It takes many months. I did collaborate with Roland Haas to convert the Einstein Toolkit into something like a library whereby we would just call the Einstein Toolkit from black holes at home. Still, there's the issue of compilability, which is not really supported on Windows, but ultimately that wasn't successful. So basically what I had to do was I had to ship out two executables, the Einstein Toolkit and black holes at home. And so black holes at home would perform the binary black hole simulation, periodically it would dump data, black hole, the metric data, 2 files, 1 per black hole, and then launch the Einstein Toolkit executable. In the Einstein Toolkit was a special thorn I had written that read in the data files one at a time, ran HFinder Direct on that, and then stored the output data from HFinder Direct to a file that Black Holes at Home would then read in. Super ugly. Of course, it was functional, and it definitely worked fine for our first binary black hole campaign. And again, the critical flaw here is the Einstein Toolkit won't compile on Windows, and that's a huge chunk of our potential market share for the volunteer computing project. So I decided to bite the bullet, and after reading a lot, of course, Jonathan Thornburg's Living Review article was absolutely incredible. I was so happy that that existed because it taught me all I know about how apparent horizon finders work, and it gave me a lot of ideas. So these ideas culminated in the creation of the Black Holes at Home Apparent Horizon Algorithm, or BAHA for short. BAHA is just another expression of my research group's core philosophy, which is to provide code to the community in an infrastructure agnostic form whenever possible. Partly this is because we straddle 2 numerical relativity infrastructures, the Einstein Toolkit and Black Holes at Home. So like I said, I introduced this already, NRPy 2. It's a code generation framework for numerical relativity. You can pip install it. And we've been able to generate some really cool stuff. One thing I haven't mentioned yet is Black Holes at Home is actually now, NRPy is actually being used to generate a highly optimized C codes kernels for a state-of-the-art gravitational wave approximant as well. So not only does Black Holes at Home inform gravitational wave approximants, it also contains within its brother, if you will, a gravitational wave approximant itself. With this, for example, we hope to ship Black Holes at Home with this approximant so that the person running the simulation will have an idea of what the gravitational waveform should look like based on previous calculations. So here's another, so of course, NRPy is one example of our core philosophy, one manifestation of our core philosophy. Another one is Grail. And Leo will talk about this, I think tomorrow, Leo Vernick. It's based on Illinois GMHD. Basically, I took all the core algorithms from Illinois GMHD, which was a code I wrote. It's in the Einstein Toolkit. A lot of people have used it, hooray. It includes the latest features of finite temperature, microphysical equations of state, neutrino leakage. We're working on M1 right now. Stay tuned for that. Like I said, Terrence added geohydrodynamic support to Black Holes at Home in only about a month, converting it from basically a vacuum Einstein equation code to a full geohydrodynamics code for dynamical spacetimes. You can learn more about and download Grail if you want at any time. GitHub.com/Grail. Grail is in the Einstein Toolkit as well, I should point out. And the Illinois GMHD in the toolkit right now actually just calls library functions from Grail to do its science. So here's Bahaha, our cute NRPy mascot. So NRPy, by the way, is a NRPa seal. They're endemic to Lake Baikal, and very cute creatures. Check out their Wikipedia page. So NRPy is these Baikal seals are also known as NRPa seals. So you kind of understand the similarity and homophones, right? NRPy is a NRPa seal. Anyway, so like I said, Black Holes, so Bahaha, we need a live apparent horizon finder, and that's the motivation behind it. We need it to work. Also, we have a supercomputer ready version of Black Holes at Home, superb, that really needs an apparent horizon finder that does not require launching the Einstein Toolkit every time, executable every time we need to find a apparent horizon. So very, very important that we roll our own to some degree. So like all apparent horizon finders, it solves a zero expansion elliptic PDE in 3 dimensions, although the PDE itself is on the surface of the apparent horizon. That is a trial surface, I should say. It finds a marginally outer trap surface. The outermost MOTS is the apparent horizon by definition. And the really cool thing, the reason why I really wanted to bite the bullet and push forward here was it actually leverages a brand new technique that's not been attempted previously in numerical relativity or in apparent horizon finding at all. It uses a hyperbolic relaxation technique to find the apparent horizon. It has this technique has the huge advantage of this technique is it is very, very robust. You give it even a terrible initial guess, and it will relax right onto the apparent horizon surface. It's lovely in that sense. However, these hyperbolic relaxation techniques are notorious for being slow, taking lots and lots of iterations to relax an initial guess to the surface. So what I challenged myself with was the following: can I make it as fast as H-Finder Direct? So here we have a 4-to-1 mass ratio, common horizon. This was found using both Baha and H-Finder Direct. What's plotted here is the surfaces found by Baha. So you have 2 inner trap surfaces. These are not apparent horizons, but they are marginally trapped surfaces. And this outer egg-shaped horizon, that is the apparent horizon. That's also known as the common horizon. If I set the same tolerances between H-Finder Direct and Baha, you notice Baha is about a factor of 10 too slow. And it's really annoying. You don't want your numerical relativity simulation to pause for 14 seconds just to find a few horizons, whereas H-Finder Direct, you only had to wait about 1.5 seconds. So Baha is about a factor of 10 too slow, bottom line. So the idea I came up with was inspired by multi-grid techniques, but it is not itself, I guess, by the mathematical definition of multi-grid, it is a multi-grid technique, but it's not the same multi-grid technique that we learn when we solve elliptic PDEs. If you read, for example, numerical recipes, it's not the same multi-grid technique. Here is how it works. You relax at a very low resolution in theta and phi. So you're resolving the horizon, very low resolution. You relax super quickly because the resolution is very low. And then you take that relaxed solution, you interpolate it to double the resolution, so 16 by 32. Then you relax at that resolution. The relaxation is going to be accelerated greatly because your initial guess is very close to the actual horizon. And then you interpolate that solution to the highest resolution, 32 by 64. You relax at that, and then you're done. With this technique alone, that sped up Baha by about a factor of 10. Actually, a bit more than a factor of 10. And actually, it's now a little bit faster than H-Finder Direct. So hooray, but I'm still a very impatient man. So I tried another idea. Some of the harder horizon finds were taking too long, and I was getting annoyed. So that attacks any apparent horizon finder. The second idea was attempt something like an over-relaxation. Now, this is, of course, it's a numerical linear algebra technique traditionally, but I thought, how about I try this with hyperbolic relaxation method? And you might ask, well, how do you do that? There's no matrix here. And here's the idea. What I noticed was that Baha, when it got in, so at first, it very, very quickly relaxes to something very close, to a surface very close to the horizon. And then annoyingly, it would asymptote to the actual horizon. So I thought, well, what happens if I just linearly extrapolate previous, and current solutions that it found, or trial surfaces, I should say, to a later iteration, and increase that later iteration until the residual, meaning the error of the elliptic PDE, is minimized. And this is the L infinity norm, by the way. So it has to be reduced at every point on the horizon trial surface in order for this over-relaxation to even pull the trigger to engage this over-relaxation. And with this technique, Bahaha with multi-grid, with over-relaxation is something like 20% faster. Now, I have to be very careful here. H-Finder Direct is not OpenMP parallelized, so it's not, I mean, it was developed in 2004. There weren't multi-core machines back then, or CPUs back then. So that we have to do all this with OpenMP to compete with H-Finder Direct. It says something huge about H-Finder Direct. It is incredible. But I did succeed in my goal of making it faster on modern CPUs.
Can I ask you something about multi-grid inspired approach? As you do relaxation and change the resolution, may I ask how the black hole properties is affected by this, like the mass or spin?
Oh,
is there any significant change in the black hole properties when you do relaxation or increase the resolution?
Yes. I mean, you converge on a slightly different mass at lower resolution than you do at higher resolution. I think that's natural to some degree, the irreducible mass. But at the highest resolution, that's what we really care about. What is it relaxing to? And you can see here on the lower left that the irreducible mass agreement between Bahaha and H-Finder Direct is about 6 significant digits. And by the way, if you take H-Finder Direct, and I think I'll show this actually on an upcoming plot, but yeah, if you actually take H-Finder Direct and all you do is you change, so in order for a pair-horizon finder to work, you have to interpolate data from your space-time grid, which could be AMR, could be black holes at home, whatever, onto the horizon trial surface, basically. So it requires interpolation. If you just change the interpolation algorithm that H-Finder Direct uses from, say, a fifth-order Lagrange interpolation to a fourth-order Hermite interpolation, then you will see exactly the same level of discrepancy. Keeping all else fixed, all tolerances the same. So this is why we say it's good enough. It's as good as H-Finder Direct agrees with itself, with just the change of how you interpolate the data from the space-time grid to the trial surface.
Thank you very much, Zach. There's a question in the chat. Robin asks, is Bahaha limited to the specific grid structure used in black hole at home or any other grid structures?
Oh, great question. So Bahaha actually already exists in black holes at home and the Einstein Toolkit. So the plan is to incorporate Bahaha into the next Einstein Toolkit release. If you were to download the development version of Einstein at home, Einstein Toolkit, right now, you will see that it will download Bahaha as well. So it's already in, as we say, the master branch of the Einstein Toolkit. And yeah, it's just, I think Peter Diener was kind enough to agree to review this new thorn. By the way, all thorns in the new thorns in the Einstein Toolkit require peer review. And so Peter has agreed to do that. So we have everything lined up. It's just a matter of getting the review done and revising Bahaha according to what the peer review says. So yeah, Bahaha, and it's also been, by the way, implemented in, I know it's been implemented in GR-Chambo as well, which is an AMR grid structure. Basically, all you need is a numeric relativity code that has an interpolator. Bahaha will tell you what points it needs to interpolate to, and you send that information to your interpolator, which hopefully is a parallelized code, and give the data to Bahaha and just let Bahaha find the horizon. It will find the horizon on that on those grid points that are interpolated to on that grid that you give Bahaha. So yeah, great question. So here the Q equals 4 common horizon find time. So I'm showing here the optimal number of core count that Baja uses. Actually haven't gone into much trouble to optimize for higher core counts. 8 is close to what we normally use anyway. And 8 cores is pretty common nowadays in consumer grade desktop computers. But it's also common with the Einstein Toolkit. But you can see here, if we just use 1 core, I guess this is the fairest comparison with HFinder Direct, which also uses 1 core. Baja's with these accelerators is almost exactly a factor of 2 slower than HFinder Direct, which, yeah, I mean, I can accept that. But going to as few as 4 cores, it starts to become a bit faster. So, and I do think this scaling can be improved. I think it's just a fact that we OpenMP parallelize every loop indiscriminately, and we shouldn't have done that because there is some overhead with that. So anyway.
And I'll just say that I think you could probably get a factor of 4 if you change the time integrator, but that's another discussion.
Maybe, yeah. Thanks, Steve. So yeah, even without OpenMP, like I said, Baja is still within a factor of 2 of HFinder Direct, which, to be honest, that was all I was going for in the first place. Just within a factor of a few of HFinder Direct, and I would be happy, just because HFinder Direct is so darn fast and just so good. I'm more than happy. Yeah, so there you go. Here is another. Oh yeah, this is very interesting. So what I did was I set the same tolerances on HFinder Direct and Baja, and all I did was adjust the total mass in code units. This is a test of how scale invariant your apparent horizon finder is. So, in other words, if the total mass of the 4-to-1 mass ratio is 10 to the minus 8 in code units, if you take the area and you divide it by m squared, that should be constant regardless of what the mass scale is. Baja is mass invariant in that case. From 10 to the minus 8, spanning 16 orders of magnitude, Baja is giving you, for the common horizon, the same area. Same with inner 1 and inner 2 horizons. HFinder Direct, though, I was not able to, I swear I tried, I wasn't able to get it to find a horizon at the smallest mass scales. And at the largest mass scales, it seemed to converge to the wrong value. But you can see it at the standard, total mass equals 1 scenario. They agree very, very well with between Baja and HFinder Direct. So in the paper, I show the gallery example of the GW150914 from the Einstein Toolkit. Here we're showing one of the horizon trajectories comparing Baja with HFinder Direct, and you can see that the error in the distance from the origin versus time is between 10 to the minus 6 to 10 to the minus 5 right near merger, which is very nice. Excellent agreement. And the question ultimately that we had to answer was, what tolerance is reasonable? Like, is this good enough? Is this bad? Is there some systematic offset going on here with Baja? I don't know. So what we did was we used the interpolation error from the numeric relativity grid as our guide. So what we did was our control for HFinder Direct was to use third order Hermite interpolation, interpolating from the numeric relativity AMR grids to the HFinder Direct trial surface, or Baja trial surface. And you can see that the relative error in the area of the horizon, this is the smaller black hole, was just a smidge above 10 to the minus 5 on average. You do the same thing with Baja, where you have the control being the third order Hermite HFinder Direct compared to the third order Hermite Baja, and you can see that actually we're agreeing better with HFinder Direct than it does with itself. at fourth order Lagrange. And yeah, in fact, that is reflected by Jonathan, who reports typical resolutions takes a few seconds to find a apparent horizon to 10 to the minus 5 accuracy. What did we just see? 10 to the minus 5 accuracy on a gigahertz class processor. Cool. So when you do look at the total time in the H finder during the in-spiral, this is something that Carpet will give you with that tolerance of 10 to the minus 5. Bahaha with multi-grid inspired plus over relaxation is about a factor of 2 faster. Again, we are using OpenMP here, so and whereas H Finder Direct was developed without that support. Here we're looking at the irreducible mass of the smaller black hole. Look how many significant digits are plotted here on the left on the y-axis before you judge too harshly. You can see these curves overlap extremely well. We also did a precision horizon find. So this is a really cool apparent horizon torture test. You want to find the largest radius where you have 3 black holes positioned in an equilateral triangle, such that these 3 Brill-Lindquist black holes share a common horizon. And what we found in Bahaha was the radius in Brill-Lindquist coordinates, this radius on the right here that ends in 9,7, it was able to find a common horizon. And the radius 1.19 blah 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 82, it was not able to find a common horizon. So H Finder Direct was run, of course, with much slower machines back then, and Thornburg reports this. So you can see we're agreeing with the state-of-the-art trusted value in the literature to 1, 2, 3, 4, 5, 6, 7, about 8 significant digits, 7 plus significant digits. So pretty happy, very, very happy to see this. It reflects that a lot of things are going right in Bahaha. So we are gearing up for the second binary black hole simulation campaign. And a lot of fun things are going to happen with that. I don't want to go into too much depth here because we need to get to the tutorial. One new innovation I wanted to share is this notion of it's called a wedge ring grid structure. So this is an actual grid here. I put gaps here so you can see that there are different grids here. So basically what you do is you take the sphere and you cut out this region up here where the z-axis is, the upper region, and you also cut out the lower region.
Hey, Zach.
Yeah, please.
Could you talk about how you handle the boundaries of these grids?
Yeah, it's inspired by Llama, the Llama code, which is the Einstein Toolkit's carpet-based multi-patch grid structure supporter. So what happens is these grids overlap. So this grid, say this we call this the ring grid. This grid is extended a little bit, and then we call the first grid points of overlap. We call those the buffer points, the buffer zones. You add exactly as many buffer zones as you need to ensure that to get information from, say, the top grid to the north grid to the east grid, let's say, and east grid to top grid, you add just enough buffer points such that you don't double interpolate when you do that information transfer. So anytime you communicate between 2 grids, of course, it has to be multi-directional. You interpolate on this grid. I don't know if you can see my mouse, but
I can see your mouse. I'm not sure what you mean by double interpolate, though.
Yeah, so you never want, when communicating information between 2 patches, you never want the result of an interpolation from patch 1 to patch 2 to be sorry, let's put it this way, from patch 2 to patch 1. So first you do from patch 1 to patch 2, okay? Then you do patch 2 to patch 1. The result of that has to be commutative.
Yes.
In other words, the result had better be 2 to 1 or 1 going 2 to 1 then 1 to 2 or 1 to 2 and 2 to 1. The result of that, those pairs of interpolations had better be exactly the same. You never want to double interpolate is what I'm saying.
Right, I get it now.
Yeah. So very early versions of black holes at home, I did have the double interpolation issues, and you would not believe the amount of numerical noise that I saw. And I worry that some older multi-patch infrastructures maybe didn't account for that, and that may be why there was some noise there. But anyway, so the wedge ring basically converts this spherical coordinate grid, which used to be 1, into 3, where you cut out the region near the z-axis, and you replace it basically with a fourth of this ring. So if you imagine this here, this is the same grid as this here. It just goes around the black hole, if you will. And then up here, we call this the wedge. It's just 1/4 of the ring being wedged in here, another 1/4 of the ring being wedged down here. So you replace the full sphere with 3 grids. That's half, by the way, what you get from cube spheres. So I kind of like the simplicity of that. I'm not the first person to come up with this idea. I found out later, at least 2 other groups had a similar grid structure idea, one being the Patchwork MHD folks, Mark Avara, for example, who called this grid structure the perfect grid structure for black hole accretion disks, because the accretion disks, if it's in the ring, it will never ever cross a grid boundary. The fluid elements will never cross a grid boundary as they orbit the black hole. That any fluid element that's in the ring will stay there. So it's going to result in very low diffusion as compared to a Cartesian grid at a similar resolution. And then in the region up here, you have another full patch in the wedge region where you can model the black hole accretion disk's relativistic jet. So it's perfect for modeling black hole accretion disks, which is kind of important for our work and modeling compact binaries with matter, like binary neutron stars or black hole neutron stars potentially. So again, the wedge ring grid structure, by removing the z-axis, there are no coordinate singularities. And that's a very exciting possibility, because for one thing, there's no grid focusing along the z-axis anymore. And so we don't have issues with our CFL, our time step being small, just because we have a spherical grid. So a lot of cool things can happen out of that. All right, good. So let's take a little bit of a break. How much more time do I have?
We have 23 minutes left, Zach.
23 minutes. Okay, great. Let's take a 2-minute break. I'll let what I'm going to do is I'm going to paste this URL into the chat.
Yeah.
So that we can all load it up easily. Just a second here. Oh, there it is. Where's my chat? Chat. Here we go. There we go. So yeah, go ahead and load it up. We don't need any special. Sorry, Steve, we didn't need your server for this one. We're going to be using my binder, which is a free resource to the community that provides something like a GitHub Actions level set of servers to run Jupyter notebooks. And what you'll see is not that. Go to this URL. You see it will launch the binder. I had it preload before my presentation. So it shouldn't take long. You can actually see the build log. There we go. And there it is. The NRPy tutorial.
then we are in 2 minutes break, right? Zach?
Yeah, let's resume at 12 past.
Yeah. Yeah.
So yeah, so please visit this URL whenever you're able. Which I also pasted in chat, so you can just click on it. Shouldn't take long, and it will just load up. This is not running on your computer at all. This entirely is running in the cloud. So when I was invited to give a talk on an NRPy tutorial, I felt embarrassed that I hadn't updated the NRPy 1.0 tutorial to NRPy 2. By the way, here is the NRPy 1 tutorial. You can see it's a lot of notebooks. All combined, this is over 100 notebooks. Some of these are just portals into a lot more notebooks. For example, let's see, where is it? Yeah, here we go, like this one. This just gets you into another, oh, why are you so slow? Okay. Yeah, a whole bunch more notebooks, basically. Anyway, so I made a valiant effort over the past week to migrate as many core key NRPy tutorial notebooks to NRPy 2, and I'm very happy with what came out of it. We have a 10-minute overview. We'll be starting here, by the way, but what I really like is, and this is key to NRPy 2, it has a very limited number of core Python modules that you need, including capabilities for C code generation, parameters for steering NRPy, as well as generated C codes, numerical grid, notions of numerical grids, index expressions, which are used to construct these highly complex tensorial expressions like Einstein's equations and whatnot in such a way that you don't end up pulling your hair out. So it's it's a huge convenience. Finite difference derivatives. So NRPy is capable of generating full finite difference kernels for, let me zoom in a little bit, actually. Here we go. Full finite difference kernels for numerical relativity codes, whereby it figures out, based on your finite difference order, what grid points need to be read in from memory. It then performs the finite difference operations to calculate the approximate derivatives at whatever order you specify. And then the subsequent code, wherever derivatives appear in your underlying expressions, it will automatically set those, basically. So you start with the expression, you tell it the finite difference order, and because of how the variables are named, it will infer, NRPy will infer what is the first derivative, what is the second derivative, what is the derivative with respect to, and automatically figure out how to read it from memory, even if it's a zeroth derivative. It automatically figure out how to read it from memory, and it supports Einstein Toolkit memory reads, as well as Black Holes at Home memory reads, and it can be extended. It's completely extensible as well. So it's nice, and that has to do with this grid here. And like I was saying, it does also support reference metrics. This notion of you choose a reference metric, that's basically choosing your coordinate system for your numerical grid. So with reference metrics, and you can see we actually support a lot. Oops, sorry. You scroll down to the bottom of this, you can see a list of the supported coordinate systems. You see the wedge and the ring, for example, that I was just talking about. SimTP, TP actually stands for two punctures. So this is a perlate spheroidal grid. The two punctures code actually uses a bispherical-like coordinate system with two foci. It supports cylindrical-like, Cartesian-like, spherical-like coordinates. Unfortunately, there aren't any tutorials beyond this right now in the current version of the NRPy 2 tutorial. Oh, come on, reload.
Zach, there is a question in the chat.
Yeah, please.
David Felipe asks, is the neutron star evolution module available in the repository? He asks Groovy version or module. Or is it possible to run a neutron star? Yeah.
Right. So Terrence is in the process of open sourcing Groovy right now. That said, we do have a initial data solver that is now in the toolkit as well, that NRPy, the Black Holes at Home, also uses. It's called Tovola. It solves a TOV equation naturally for setting up neutron star initial data. Black Holes at Home also has an example. So if we just go to the NRPy repo, go to NRPy. Sorry, at some point, all these examples will be in the NRPy tutorial, but here are a list of the many examples that fully work and just you can play with. Black hole spectroscopy, generating carpet X thorns. This is the one that you could look at. This is the hydro without hydro test, which is a pretty neat test. So if you're familiar with the Cowling approximation, that's an approximation whereby you fix the space-time metric, you fix g mu nu, if you will, and you only evolve t mu nu. That's a Cowling approximation. Well, this is the opposite of that. You fix t mu nu, and you only evolve g mu nu. It's not exactly long-term stable, but it is a great code test to confirm whether you've implemented the stress energy source terms in your Einstein's equation solver correctly. And that's really the purpose of this. But yeah, so this one actually sets up a TOV on a numerical grid and performs a hydro without hydro test. But yeah, we definitely plan to have a full working groovy version. I would say within the next 3 or 4 months. And that's based on the fact that Terrence is staying with us until about next August or so. He's about to graduate. He successfully passes his defense, hooray. But yeah, that is very high on his priority list, open source Groovy. So I hope that helps.
Congratulations to Terrence, and thank you for your answer. And there is another question in the chat. Kate asks, the grid rotates with the black holes, but how does it change as the black hole approaches each other?
Oh, that's a great question. Oh my gosh. And I have a really cool movie that shows that off. Let me see if I can find it. Gee whiz. Actually, this. Yes, I think this. Let me see. I have a really cool movie that shows this off. Let me see. Yes, here we go. Cool. Okay, so this was circa 2023 work, actually 2022. So you start out with this. Here, let me zoom in here. All right, so you start out with this grid structure that you've already seen before. It's actually 7 patches. This has to do with how we did this, but you can see that when the 2 black holes get too close, so this lower, it's actually a Cartesian, it's a rounded Cartesian grid. That's what we're seeing here. That's why they look round. They're rounded Cartesian grids. So the problem is this upper sort of big rounded Cartesian grid we don't have the communication. At the time, we didn't have any communication infrastructure in place such that this grid could communicate with this grid down here. So when 2 black holes got too close, oops, stop it. Then we had to move to a different grid structure. And this is what the grid structure looked like. Basically, it's like, okay, well, we can't do rounded Cartesian surrounded by a spherical grid. So we're just going to migrate to a cheap AMR grid, basically. And so that's kind of the answer. And here on the left, you'll see exactly how the grid adjusts over time. So here we have the 7 grid with the rounded Cartesian grids there near the black holes. You'll see they're getting closer, and watch the grid structure change. Boom. So that's the live grid structure change. And you notice that it changes very, very rapidly. And of course, I was very worried about how quickly this happened, that maybe this might result in a big jump in constraint violations. And so here I'm going to show on the right the log base 10 of the Hamiltonian constraint violation. And you can see very early on, as I've said before, there's a big burst of a constraint violation that propagates out early on. But you can see we're very, very low constraint violation here. This looks quite favorable compared to Einstein Toolkit grids, for example, or Cartesian AMR. And you can see as the grids change, watch the constraint violation, it stays dark, which means it stays low. I was actually very surprised to see that there was no jump. In fact, there's a drop in constraint violation as the two black holes come together. So very happy about that. I hope that helps answer your question.
Thank you, Zach. May I ask what triggers the change in grid structures at that point? Because as far as I see, they don't touch, right? They don't merge. It happens before the merge.
The question is why do we change the grid structure?
What triggers, for example, in the simulation, what triggers the change in grid structure?
Oh, because yeah. Great question. Yeah. So that's easy. Basically, the multi-patch infrastructure, if it returns an error code, then it's unable to find what it searches for is, am I able to fill in all of, stop it. Okay. Am I able to fill in all the data, say on this lower rounded Cartesian grid using only data that are in the interior of this spherical grid just outside of the small spherical grid down here? If that turns out to be false, then I need data that's in the buffer zone, actually more specifically the ghost zone of the interpolation ghost zone, whatever, of the spherical grid, then that's a failure. So it just searches for a failure. When a failure mode is returned, it will automatically move to the Cartesian AMR-like grid structure. So it's looking at how information propagates between the patches.
Yeah, thank you very much. Yeah, thank you.
Yeah, so anyway, back to this. I only have about 5 more minutes. All right, let's take a 10-minute overview in 5 minutes. We're going to speed run this. All right, so this shows off a little bit of the capabilities of NRPy. The same existed, by the way, in NRPy 1.0, but this has been updated completely for NRPy 2.0. So as it says here, one of the problems that we have is not necessarily that the numerical techniques are like super complex compared to what other groups have to deal with, but it's that the equations that we solve are just incredibly complex. So complex that sometimes we cause compilers to crash. So Einstein notation makes our complexity more manageable. Hopefully we're all familiar with that, and if not, you can always click there and learn more. Yeah, so basically it's really cool. It's almost like Einstein notation is a type of code itself. And when you express the code, you could actually express that code in NRPy's native Python language. So you construct a rank 1 tensor as a list of SymPy expressions, rank 2 tensors as lists of SymPy expressions, and so forth. And implied tensor summations are simply loops. You just loop over to construct whatever tensorial expression you need. Do any implied sum that you need to do. It's really quite convenient. And so NRPy combines this idea with SymPy, and in it, it takes the resulting expressions that can be absolutely gargantuan that are constructed as a result of implied tensor summations and so forth. And SymPy, in spite of the fact that these expressions sometimes, just to express them, it's over a couple megabytes just in terms of data structures. It's able to quickly and efficiently optimize those expressions. And so, yeah, NRPy builds on the idea of learning by example. That's what the whole point of the NRPy tutorial is. Actually, this is the NRPy 1.0 repository. It contains pedagogically and well-formatted Jupyter Notebook tutorials. Well, now we're doing that in NRPy 2. Okay, so let's start with constructing the three Christoffels, also known as the connections to the spatial 3 metric. So Christoffel symbol of the first kind is defined as this. So what we're going to do is, and this is highly recommended anytime you write NRPy code, you put the expression right above where you want to write it. Actually, this is not good because I didn't, where did I put it? I'll build it down here. Yeah, okay, I'll do it again. Yeah, perfect. Okay, so first things first, we're going to define the 3 metric, spatial metric, and its inverse using core NRPy functions. So here's how you do it. So IXP, that's the index expression module in NRPy. Declare rank 2. gamma DD is the base name of that. Symmetry, you're going to set the symmetry of that metric tensor to 0, 1, meaning it's symmetric in its 0th and 1st index. And it's a 3-dimensional tensor. Cool. Gamma UU can then be automatically computed using our symmetric matrix inverter, which is a super quick way of inverting your matrix. So we just plug in gamma DD to get gamma UU and the determinant naturally, because that's part of calculating the inverse. Okay, and now we have here gamma DD 0, 1. We're going to check that it's equal to gamma DD 1, 0, and you can see that indeed when you print out gamma DD 0, 1, you get gamma DD 0, 1, the variable name, and gamma DD 1, 0 is also gamma DD 0, 1. So it's the same symbol. Therefore, they are this metric, at least these two 0, 1 and 1, 0 are in fact do reflect that symmetry. An exercise, one exercise to the student here. Verify that gamma down, down, gamma up, up is equal to, in fact, the trace 3 of the metric. You can put that together pretty quickly for I in range 3. Oops, sorry, I pressed the wrong button. For j in range 3, I'm going to put in here sum equals 0. And that's going to, sum is going to, dang it, keep pressing the wrong button. Okay. Sum is going to represent our trace, and we're going to say sum plus equals gamma DD ij times gamma UU ij. Keep pressing the wrong thing, sorry. What am I missing here? Oh, of course, I haven't run this cell up here yet. Oops, there we go. Okay, there, we had to run that cell first. Okay, now constructed the sum. Now we're going to print sp.simplify sum. Shift enter. Oops. Close my bracket parentheses. And there you go. Here it is. 3. Just exactly as we hoped. Perfect. Okay, just one check. And now here is how, for example, you can construct tensorial expressions. And you'll see that the symmetry here is just gorgeous. I love this. So gamma kij involves some implied sum. Sum over L. Oh, that's it. Sum over L. That's fine. So what you're going to do is you're going to set gamma u dd, gamma up, down, down, kij, upper K, right? U corresponds to the upper, dd is the lower, ij, plus equals sp rational 1/2, so it's just 1/2, times gamma uu, notice kl times, in parentheses, gamma dd, and it's underscore dd. That's how we represent derivatives in NRPy. And when you represent it, quantities this way, NRPy's finite difference code generator will recognize that and realize, hey, I need to generate a finite difference derivative. In this case, first derivative, lowercase d derivative, and then d, that is the order of the derivative. So gamma dd dd jli, as you can see, it's exactly as written here, plus ilj minus ijl. Boom. Okay, cool.
Zach, we are in the last minute, but I think this is very useful for the students.
Yep. So let me just
if you would like to continue for 5 minutes, you can do that.
Oh, that's very kind of you. Yeah, so I just wanted to let me just zoom through this really fast. So for one thing, we can confirm that it is in fact symmetric in the last in the lower indices, even though we did not specify that at all. It just naturally happens, of course, because of its definition. And now here is where the magic happens. When you call NRPy's ccogen code generator. So all you have to do to make this work is declare a symbols list and declare a list of variable names. So here's your symbols list, gamma ud ijk, and here's your variable name list. We're going to call it Christoffel udd, and we're going to use string 1, a search string I, so it's going to be 012, J012, and K012. And then we just import the NRPy C code generator, and we call it with symbols list, the variable name list. And we're going to disable optimizations first, just to show you the consequences of your actions if you choose to disable optimizations or don't write the code in a very efficient way. And yeah, so here's what you end up with. So you see here's our first expression right here. Christoffel UDD000 is equal to, and this is all of those terms just expanded out. 0, 1, 0, 0, 1, here it is again. So you see there's a lot of math to compute these connections. It's ridiculous. So now what we're going to do is we're going to use common subexpression elimination. And you can learn more about that here. So for example, you have in the Wikipedia article, A equals B times C plus G, and you need to compute both A and D. Well, what do? Well, it would be waste to compute B times C twice. So instead, we're going to declare that as a temporary variable and then just declare A equals that and D equals that. So there you go. NRPy does a lot of fancy footwork under the hood. It enhances SymPy CSE capabilities. And here's what happens when you enable CSE. You'll see these temporary variables appearing, which represent patterns that it found in these huge expressions up here. And it's decided because it saw the pattern at least once or twice, sorry, at least twice or 3 times sometimes if you set the parameter appropriately. And then look at what happened to this gigantic expression. It all boils down to, when you CSE, that's it. It's a reduction of more than an order of magnitude in number of floating point operations just by declaring some temporary variables. And this is all valid C or C++ code right here. Now let's go to optimization level number 2. And now what we're going to do is we're going to take advantage of modern day CPU special features. This is as close to assembly language as you ever want to get. So I'm enabling CSE, but what I'm going to do is I'm going to wrap all these into, these are actually C macros that are C++ macros, identical, that will replace this with the actual assembly instruction effectively for doing this. And what this enables you to do is evaluate multiple, when you're doing this on a numerical grid, you can evaluate in one CPU cycle 4 different grid points worth of data. So a multiply, for example, would multiply these guys, these two, gamma DD12, gamma DD12, would multiply this on 4 grid points in one fell swoop. So it's a huge improvement in performance by using this. Another really cool thing is this notion of a fuse multiply add or fuse multiply subtraction. That's actually contains, each of these operations contain 2 full floating point operations, a multiply and an add, or a multiply and a subtract. And it does that in approximately 1 CPU cycle. So it gives you 2 for 1, a 2 for 1 deal. Really amazing. So you really want to search. So what NRPy does is it searches really hard to find as many of these fuse multiply adds and subs as it can when constructing these expressions. And you can see, there you go. If you add up all these, it's actually fewer floating point operations because of, fewer CPU cycles because of both the multiplicative thing you get from SIMD. So multiple modern CPUs can do either 4 or 8 double precision operations in a single cycle, which is pretty awesome. With SIMD, you multiply by another factor of 2 in terms of floating point operations, which is really cool. All right, so another thing you can do with CCogen is actually use generate finite difference kernels. So we set the order, we set the infrastructure. So we're going to use, this is called the ET legacy infrastructure, also known as Carpet, not Carpet X. And actually, this would work just fine with anything Cactus, to be honest. It's general enough. So we set that, we register the grid functions, the Christoffels as grid functions, so that we know how to store them in memory. And the gamma DDs, we also register as grid functions, so we know that these are accessible on our numerical grid. They have a symmetry property, and you can see we're now going to do 6th order finite differencing to compute our Christoffels. And here you go. So we're reading gamma DD00 at I minus 2, J minus 3. I minus 2, I2 minus 3. Sorry, this is I2. So this is K minus 3. So there you go. I2 minus 2 and so forth. So you can see we're reading in the data from memory. That's step 1. And step 2 is actually computing the finite difference derivatives. All the coefficients are automatically computed in NRPy. And then step 2 is to evaluate the SNRPy expressions and write to main memory. So here we're doing the computing the expressions and writing them to main memory. Christoffel, remember we declared these as grid functions. So you can see here CCD, blah, 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 blah. This is all standard Einstein Toolkit notation. So what's next? I encourage you to try it out, play around with this. By the way, you can run any of these notebooks by just clicking the fast forward button, clicking restart, and it will run every cell. So you can modify any cell that you want. You can play with it. I encourage you to try it out. It's really handy dandy. Yeah, that's all I have time for. Thanks everyone for your attention. And thanks again for the opportunity to talk about this. It definitely motivated me to get the NRPy 2 tutorial. The NRPy.
Thank you very much, Zach. It was very informative. I think everyone benefited from this. Thank you very much.
Yeah, thank you so much.
Stop the recording.